Alright everyone, welcome to my second video, and in this video I want to highlight a tool that I made for encrypting shellcode with RC4 or XOR, and then show you guys the impact that the tool has. Now I want to preface this by saying that this tool is, it's very simple. It's nothing complicated, it's nothing mind-blowing, but it's just another piece of automation that I think will ultimately make my life easier. So if you remember from last video, we had generated shellcode for spawning a calculator. And then when we tried to compile a Rust program with this shellcode, we got an error, which I'll show you again. So we paste it in. No, that's not right. I guess I didn't copy. So let's copy this. Paste. Yep. Let me just fix that real quick. Tab that over. Okay. Good enough. So if we try to run this, you see we get the alert and we get the error, right? And we talked about how since the shellcode is not encoded, we're just going to have to deal with that. And the way we deal with that is with encoding. So this program will take care of that for us. I'll show you how it works. Python 3 encoder. We have two options, XOR or RC4. So we can start with RC4. We enter our shellcode, and the program expects the shellcode to be in this format. And I think expecting it to be in this format is fine because this is how MSF Venom does it, right? So now you can use any MSF Venom you want with this tool the tool that I'm showing you right now. So you paste it as one line, new line characters at the very end here. And we enter our key to use, YouTube. And then it'll give us our encrypted shellcode. So if we take this encrypted shellcode, copy that, and we paste it here, semicolon. Now we no longer get that error. So through encryption, we've evaded one layer of static analysis of Windows Defender. It's no longer able to say, yep, that's shellcode for opening a calculator. I have fingerprints on that, signatures, whatever. I know what that means. I'm gonna not compile this code or throw an error, and then the compiler will say, oh, there's an error. We're not gonna let you run the program. Okay, so now that we've shown that the principle works, we have to verify the encryption. So doing that for RC4 is a bit more of a pain than I care to do. So I'll show you with XOR. We choose XOR. We need our shellcode one more time. Copy that. Paste as one line. Key. So for the purpose of verifying that the encryption worked properly, I'm going to do a 1-byte key. But this program does support a key of arbitrary length in ASCII. So we have this, right? This is our ciphertext, our encoded shellcode. So let's verify the encryption worked correctly. Python 3. So key equals a ciphertext equals 0x BD. We're just going to verify that the first byte encoded correctly. So ciphertext is BD and plaintext equals, so the first byte of the plaintext was FC, 0x FC. Now if we do ord key XOR int plain text 16, wrap all this in hex, we see that the encryption is working properly. And if you were to do int ct 16 XOR ord key hex, you'd see we get the same thing back. So we know that our encryption is working. And just to show you that it works with the arbitrary length key, we'll do it one more time. There you go. So we'll go over the code real quick. Main function. We have a utils class and an encoder class. The utils class is basically just things that the rest of the program needs, general functions that can be used everywhere. The encoder handles the RC4 and the XOR encoding. So print out the options, make sure the user isn't choosing a negative number for an option or something that's not available. Read in our shellcode, then we call parse shellcode. Parse shellcode is part of the utilities class, which is right here. It'll make sure that the user didn't enter nothing. It'll make sure that the bytes are comma separated, and then it'll just convert the string of hexadecimal bytes into a array of integers. And you want it to be an integer so then you can do XOR and any other mathematical operations that you would want. So that's after that, we've parsed the shellcode, read in the key, ensure it's not nothing, configure the encoder, and then we just encrypt the shellcode. And the encryption method is just two if statements. XOR, the only nuance here is that, or not even nuance, it's not even the right word. The only important detail here is that you have modulo length of the key. This is for if you need to cycle your key more than once, because if the key, like we said, if the key is smaller than the plain text, you have to cycle it. So that's what this will do, because X loops over the length of the shellcode. We do the XOR, and then we add our encrypted byte to our encrypted shellcode. I put this verify encryption function in here. It's part of the utils class. Now that I'm looking at it, I think it's redundant because it's basically just doing the same thing again. But yeah, I should probably take this out. But I threw it in there. It seemed right to me in the moment, but now I'm realizing it's probably just wasted code. Anyway, RC4. Here's the RC4 implementation. I basically just looked at the C code that we wrote last time and converted it into Python. It's obviously a bit easier in Python. I'm not going to really explain this if you are just watching the second video. The previous video before this explains how RC4 works in more detail. But yeah, there's RC4. And then after that, it basically just formats the shellcode properly and prints it out to standard out. And so more high level, the way that the flow of this stuff is going to go is you generate or you write your shellcode. You take your plaintext shellcode, encrypt it with a tool like this, or encrypt it in a different way. You then throw that encrypted shellcode into the C program, the Rust program, any systems language program, right? And then that's where the decryption will happen. So you notice there's no decryption anywhere in this program, and that's because the decryption happens here. This is your ciphertext, but you're not able to run this. If you try and make a function pointer that points to the address of this buffer in memory, and then you try and execute it, you'll get a seg fault or something because these aren't valid opcodes. These need to be decoded in order to become like what they originally were from the output from MSF Venom in order to be run and executed. So inside of the Rust program, C program, whatever it is, you will write a decryption stub that will decrypt the shellcode, create a function pointer, and then execute or invoke that function pointer and then run the decrypted shellcode. And then after, I guess the benefit of this is that the decryption will happen at runtime, right? Like you don't have the plain text shellcode just sitting on disk, sitting inside the file. What's actually sitting there and staying there is the encrypted shellcode. So anything that scans it will see that it's encrypted, and then it'll get decrypted at runtime. So theoretically, it's vulnerable to memory scans, but that's a problem for later. I just wanted to highlight that we no longer have to deal with this error. So in the next video, I don't know if it'll be 1 or 2 videos later or what, but what we're eventually going to build this out to is, like I said, decryption and then executing the shellcode. After we're able to understand how we execute shellcode, then we can jump into stuff like other evasion methods, more complicated malware, etc. So yeah, that's it for today's video. As always, if you have any suggestions on code optimizations or anything I did wrong with the code, let me know in the comments or otherwise. If anyone is interested in this code, I can put it on GitHub or something, but honestly, it's pretty simple stuff. Nothing here is super complex. It's mainly just a tool for convenience it's not really a tool for doing anything innovative or super exciting. It's more so just automation and convenience. All right, I'll leave you guys with that. I'll see you in the next video.